Sir, is there any noise coming when I'm talking?
Today, no. Last lecture, yes.
Okay, okay. So that's why I asked.
Yeah, today it's much better. There's no noise. Okay, so now we are recording. Um, Good afternoon or good evening, everyone. So, last lecture we were in the midst of proving Thomason's theorem, right? And once we prove Thomason's theorem, we immediately get this consequence, right? Which is a generation theorem for three connected graphs. Right? So it depends on in the sorry, okay. In the forward direction, it depends on Thomason's theorem, and in the reverse direction, which is much easier, it's theorem 9.12, which was basically a do-it-yourself exercise. Okay, so the difficult part is Thomason's result, and in order to prove Thomason's result, we prove this lemma 9.11, which basically tells you when is an edge non-contractible for a three connected graph with at least 5 vertices. Okay, so if it is not contractible, then we got this structure that the two ends of that edge participate in a three vertex cut with another vertex. Okay, and then inside the proof of theorem 9.10, Thomason's result, what we did is we chose an edge and a vertex.
Sir, I have a question.
Yeah.
So is the converse of lemma 9.1 on true? Means
What is the converse of lemma 9.11?
so
I
basically,
see. I see. Um, well, I'll let you think about that. Okay. So if an edge participates in such a structure, then does it necessarily mean that it is not contractible? Okay. So you can think about the converse. This is a good exercise. Try it yourself. We don't need the converse, so we won't worry about it right now. Is the converse true? So that's a good question to think about. Okay.
so
Good.
if the converse is true, then it will be a characterization of non-contractible edges
That's right. Exactly.
in the three-connected graph.
Okay. Good. So now we are taking a three connected graph and we want to prove that there is an edge that is contractible. So let us suppose, for the sake of contradiction, that no edge is contractible, right? So we know this structure from lemma 9.11. So we will choose an edge E and a vertex W in order to maximize a certain parameter. And that is going to help us in reaching a contradiction, right? And the parameter we are maximizing is we are looking at all the components of G minus UVW because this is a three vertex cut. And we are maximizing the number of vertices in the biggest component. Okay. So among all choices of E and W, we are going to choose E and W so that we get a component that has as many vertices as possible after removing the vertices UVW.
So, sir, the maximum we are getting is basically over all such EW pairs.
Exactly. Right. Okay. You can even think of it as all triplets E, W, comma, E, comma, W, comma, J. Okay. But I wrote it in a different way, but it's basically the same thing. Okay. So we are maximizing over all EW the size of the biggest component after deleting UV and W. Okay. And now we want to get a contradiction to the choice of the edge E and the vertex W. Okay. So that is what we were doing. And there was a certain strategy behind it, which I won't go through again. I hope you have all gone through the proof again. So we were at this point. This is the drawing you want to look at. We have the edge E, we have the vertex W, and we chose an edge F joining W to some component L, which is different from J, which is the biggest component, right? So that is our edge F. So this edge is also not contractible by our hypothesis because no edge is contractible. So this edge, along with some vertex y, we will get a 3 vertex cut wxy. Ananya, you have a question?
Yes, sir. So my question is, so basically, here J is the largest component of G minus UVW, right?
G minus UVW, yes, that's right.
Okay. Okay. So the largest component may not be unique
It may not be unique. If there is a tie, you break tie arbitrarily.
arbitrarily. Okay.
Yeah,
So the choice we are breaking during the tie, that is not important.
that is not important.
So we can break the tie arbitrarily, right?
Yeah, yeah, you can break the tie arbitrarily. It
Okay, sir.
doesn't
Okay.
matter. Yeah.
Okay, sir. Okay, sir. Fine.
Okay, good, good. Okay, so now we take some component that is different from J and we choose this edge joining W and a vertex in that component. We know such an edge exists. That was a do-it-yourself exercise. Okay, and our claim is that this edge F along with some vertex Y, we don't know where Y is in this drawing, it doesn't matter. This will contradict the choice of E and W. Okay, that's what we were trying to prove. So T is the set Wxy, the ends of F and some vertex Y. And the claim is that in the graph G minus T, there is a component that has more vertices than J. Okay? Are there any questions or concerns at this point? Okay, so this was a try it yourself problem, which means we will do it here for the sake of everyone, in case there are those who did not finish this proof on their own. Okay, so this is what we want to prove.
Sir,
Yeah,
can you just once again repeat what T is?
T is the set Wxy, the ends of the edge F and some vertex Y, which we don't know where it is in this drawing.
So Y may be in any of the components.
Y could be anywhere. It is
Okay.
not W and it is not X. That is all I know.
Okay, 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 sir.
Yeah? Okay, good. So if we prove this claim, then does everybody agree that this finishes the proof of Thomason's theorem? If you don't agree, then this is a good time to ask. Okay, fine. So we just need to prove this claim, okay? And then we will be done with Thomason's theorem. So let's go back to this drawing. Here is what we are going to do. We are going to look at this red colored subgraph. Okay? Let us look at this red colored subgraph. It is the subgraph induced by the vertices of J and the vertices U and V. Okay? So it includes the edge E in particular. This graph, I want to prove that this is two connected. Okay? Why is this good? Supposing this is two connected. The vertex Y could be here. If it is here, then after deleting Y, this graph will still be connected. This graph, let's call it H. Okay? So this is the graph H, which is induced by the vertices of J, union, U and V. Okay? We will prove that this is two connected. Claim this is two connected. If it is two connected, I can delete a vertex and the graph will still be connected. So if the vertex Y is here, I can delete it and this will be a connected graph. Notice that W and X are not in this graph. What does that mean? That means that I can delete W, X and Y and I will have a connected component that will have at least one more vertex than the number of vertices in J. Okay? So let us
I think
complete. Yeah, go ahead.
we at least two more vertices.
At least one more because Y could be there.
Okay, okay.
Okay? Let H be. H is the graph induced by the
So
vertices of.
we are assuming that Y is belonging to that induced subgraph, right?
We are not assuming that. It doesn't matter. If y is there, we will have at least one more vertex. If y is not there, we will have at least two more vertices. In both cases, you have a contradiction.
Contradiction.
Okay. So, claim, claim inside the claim, it is that H is 2 connected. Okay, I will prove this in a few seconds. Okay, what does this mean? This means that H minus Y or H is a subgraph of some component of G minus T. I say H minus Y if the vertex Y is in H. If it is not in H, then H itself is a subgraph of some component of G minus T. Okay? In either case, so let me call this component K. In either case, the number of vertices in K is at least one more than the number of vertices in J. Okay? Because H includes J, it also includes two more vertices, U and V, and now we are deleting one vertex, Y, if it is in this H. Okay? So in both cases, we will have at least one more vertex, and that will be a contradiction to the choice of the edge E and the vertex W. Okay? So this finishes the proof. The only thing I need to now convince you is that this graph H is 2 connected. Okay? So let us make some space here. Proof of this claim. H is 2 connected. Can anybody tell me why H is 2 connected? How would you prove that H is 2
Because
connected?
H union S is itself 3 connected.
Why?
H union S is 3 connected.
Why H union S is 3 connected?
Because a 2 cut of H union S will give you a 2 cut of G. 2 vertex cut.
I see, I see. So you are saying that if you take H along with S, are you taking the subgraph induced by S?
Yes, yes.
Okay, okay. Okay, so you're taking the subgraph induced by all the vertices in J along with S.
Yeah, J
J
union S.
union
Not
S.
H
You mean
union
J
S.
union S. Yeah, I get it.
Yeah, J union S.
I see, I see. Okay, that is one way to prove it. Although you will have to verify the details, right? So there is another way to look at it. You consider the graph G and you delete the vertex W. Okay? Because the original graph is 3 connected, if you delete one vertex, your remaining graph is still 2 connected. This was also a do-it-yourself problem in the last lecture. I put it on Piazza. Okay? So G minus W is 2 connected. Does everybody agree? So if G minus W is 2 connected, now UV is a 2 vertex cut in G minus W. Okay, let's write this down. So G minus W is 2 connected because G is 3 connected, and UV is a 2 vertex cut in the graph G minus W. Okay? So if you have a 2 vertex cut, then you can use the theory from 3 connected graphs part 1. You can take the UV components of this graph. They will be 2 connected, the marked UV components. What is a marked UV component? You take the graph induced by J and UV and you put a new edge between U and V. But that will be a parallel edge, and parallel edges do not affect 2 connectivity. So you don't need to put the parallel edge in this case. Okay? This implies that the graph H...
Basically, any cycle will be contained either in a unique marked S component.
That is not true. A cycle can span 2 marked S components. That is true in the theory of 2 connected graphs or non-separable graphs. A cycle does not have to be contained in one of the components. You could easily have a cycle that goes between J and L in this drawing.
No. Yeah, that may happen. But my point is that if there exists such a cycle which spans two components, then using marker edge and using some portion of that cycle, I can always get a cycle which is contained in one of the components.
Right. That is true. So that is related to the proof of this particular lemma that we
Exactly.
discussed earlier.
Exactly.
Okay.
Because ultimately we are going to prove two connectedness. So basically,
Right.
we should any two vertices lie on a common cycle.
Right. So note that H is basically a marked S component, a marked UV component of G minus W after removing one parallel edge. Okay? After removing a parallel edge joining the vertices U and V, which would be your marker edge as we discussed 2 lectures earlier. Okay? But parallel edges do not affect two connectivity. Okay, I keep making this bigger. This implies that H is two connected. Okay? So that proves this claim that the red subgraph is two connected, and once we know that, we can complete the rest of the proof as we have done here. Okay? So this finishes the proof of Thomasons theorem. Okay? Are there any questions or concerns at this point? Is there any part of this proof that is not clear? Okay, so this is basically the drawing which has all of the important information. So when you revisit this proof after the lecture, you want to keep this drawing in mind. It has all of the important features of this proof. Ananya?
Yes, sir, I have a question. So basically, in case, so basically H is the induced subgraph on G on U of G union UV. So there are two possible cases we have encountered. So either the vertex Y
Hmm.
is in the graph H or Y does not belong to the graph H.
Yeah,
So if
right.
Y belongs to graph H,
Hmm.
then we are simply removing the vertex Y.
Yeah,
And since we have proved that H is two connected, then H minus Y will be one connected. Means H minus
connected.
Y will be connected. And so we can argue, but what happens Y does not belong to H?
You tell me. You tell me what happens if Y doesn't belong to H. Try to complete the proof on your own. Tell me. So if Y doesn't belong here, then where is Y?
Y will be either in some other component.
Yeah, it could be another component, right? It would have to be in another component.
Yeah.
Okay. And you're also assuming that Y is not U and V, right? It is not in H. Okay. Right.
Yeah.
So now what happens? How will you arrive at a contradiction from here?
So we can take any vertex other than U or V in H.
Hmm.
And if we remove that vertex from, so let that vertex be Z. So,
Why are you removing a vertex? What are you trying to prove? You are trying to prove that the graph G minus the set of vertices T has a component that has more vertices than the number of vertices in J. You agree? Supposing
yeah,
J has
exactly.
5, supposing let's say J has 5 vertices, okay?
5 vertices, okay.
Fine. So you are trying to prove that G minus T where T is equal to Wxy has a component that has more than 5 vertices.
Yes, sir.
Okay. So how will you convince me of that? So we are looking at the case where y is not in H. Can somebody complete the proof? What happens if y is not in H?
So,
Yeah, Krishnan, go ahead.
yeah, in that case, the whole of J will be contained in the connected component of G minus T.
Whole of J or whole of H?
Sorry, a whole of H.
H, exactly. The whole
H
of H will
will
be
be
a subgraph of some connected component of G minus T, because W and X are not in this red colored subgraph and Y is somewhere outside. It doesn't matter where Y is, right? But when you delete W, X and Y, H is unaffected. So this is still going to be a subgraph of some component of G minus T. And so now you have a component with at least 2 more vertices than J, because you also have the vertices U and V. Okay? Aranya, does that make sense?
Yes, sir. It is clear to me now.
Right. So that is the reason I wrote H minus Y or H, because this takes care of both the cases. Okay? Good. Any other questions or concerns? Right? So technically there are 2 cases here, but if you write it in a certain way, you don't need to break into 2 cases. Your argument takes care of them simultaneously. Okay. So if there are no questions or concerns, is everybody convinced that we have proved Thomason's theorem?
yes.
Okay, good. So this is quite a different proof from any proof we have seen so far, right? I mean, it's fairly more sophisticated than all the proofs we have seen so far in this course, with the exception of maybe Menger's theorem. That was also quite sophisticated. But that was a sophisticated use of induction. This is a sophisticated use of contradiction. And one of the techniques that is used here is maximizing or minimizing a certain parameter. Okay? So that you can arrive at a contradiction. Okay?
Sir, why exactly did we discuss decomposition graphs?
Sorry, what is your question?
Why did we exactly discuss the decomposition graphs?
Which decomposition? You mean this last part?
Removing the 2 vertex cut and getting marked component.
Right. So we wanted to prove that H is 2 connected, right?
No, not this. Means we had done it earlier, right?
Oh, I see. Well, basically what happens is, so what happens in many problems in structural graph theory is that you're trying to characterize some class of graph, for example, or you're trying to solve some problem, right? Then you can reduce it to graphs that are more and more connected. So the first step is to reduce the problem to connected graphs, right? In most problems, you would have seen on assignments that you can restrict yourself to connected graphs. Do you agree?
Okay, so we're reducing everything to 3 connected graphs.
Right, which happens in many problems in graph theory. So that is the reason the theory of 3 connected graphs is really important.
Okay, I see.
So that's the idea. So the part 1 of this theory is used in reducing the problem to 3 connected graphs, and part 2 of this theory is used in solving the problem for 3 connected graphs.
So I think this theorem is really very deep theorem.
Yes. And you will see its usefulness in plenarity in module 3.
Okay, okay. Okay, so basically this theorem has many applications in planarity.
Not just planarity, it has applications in planarity, but in many areas of graph theory. And it is also a prototype theorem for other theorems in other areas of graph theory. So I work in matching theory, where you have lots of results which are inspired by Thomason's theorem.
Okay. Okay, sir. Okay, sir.
So one of my intentions with this course is to show you a collection of results that sort of they are prototypes for many results in current areas of research in graph theory. Okay,
Okay, sir. Okay.
including proof techniques. All right. So we have finished proving Thomason's theorem, and I want to go back to this consequence. It gives us a generation theorem for three connected graphs. Okay. What is it saying? For any three connected graph, you can start from K4 and you can keep adding edges or expanding vertices to construct your desired three connected graph. There is always some sequence by which you can construct your desired three connected graph. Okay? And if you are going in the reverse direction, you can keep deleting edges or contracting edges to get to a graph on four vertices, which will basically be K4 with multiple edges. And then you can remove all the multiple edges and you will get K4. Okay? So all three connected graphs can be generated from
I have a
K4.
question, sir.
Yeah.
I have a question. So is it possible that, so suppose G is a three-connected graph. So
Mm.
by this already we know that there will exist a sequence which satisfies these properties 1, 2, and 3. So is this sequence unique?
By no means.
Okay.
You can
So they are getting,
find,
okay.
yeah, yeah. You can try some slightly big example. If you take very small examples, it might be unique. But if you take a slightly big example, something like the Peterson graph should work, I think. I'm pretty sure you'll be able to get two different sequences. Right? By different, I mean the lengths might also be different. The lengths will not be different because you're always adding one edge. So the length is unique, just like your decompositions, which will be proving on your assignment. But the specific graphs you get in the sequence, they need not be unique.
Okay.
Okay?
So the length of the sequence will remain same, but the graphs, intermediate graphs will change in the
Right.
sequence.
Exactly.
Okay, okay.
Right? So the graphs will not be, the collection of graphs will not be isomorphic to each other in the two different sequences.
Okay. Yeah, yeah. So basically, sir, also, sir, I have another question. So for your decomposition, you proved the result that if G is a non-separable graph and H is a non-separable subgraph of G, then there exists a near decomposition of G
Mm,
in which the element H occurs.
right,
So
right.
is there a something kind of similar? I think it will also hold here.
It is true. It is actually called Seymour's splitter theorem, but we won't be discussing that here.
Okay,
So
okay.
I might tell you a little bit more about it next lecture. But right now, so the answer is, the short answer is yes, something similar exists here.
Okay. So if G is a three-connected graph and H is a three-connected subgraph of G,
No, you
then
can't take a subgraph. You can't take a subgraph. You have to be more careful because notice that in this sequence, the graphs are not necessarily subgraphs of the original graph. Right? Just to give you one example, you go back to the original example here. Notice that this graph is not a subgraph of the graph above it.
yes, sir, yes, sir. I understood your point. The graph
Okay.
should not be subgraphs. Yes, yes, yes,
Right.
yes, sir. Yes, sir.
So there is a term for it. It's called minors, but I will define it later. I will define it in the next lecture, maybe. Okay. So instead of subgraph, you use the concept of a minor, and then you get a similar theorem due to Seymour.
So basically, if H is a three-connected minor of G, then we can
That's
say
right.
that there exists a sequence. Okay.
That's right. That's right. Yeah. Okay. Good.
What is the name of the theorem?
Seymour splitter theorem. So let me write it
Simon's
here.
Splitter theorem. Okay, Simon's Splitter
Yeah.
theorem.
In fact, it is a stronger version. If you're interested, you can read it.
So will you discuss this theorem in this course?
No, we won't.
We won't.
No, it's beyond the scope.
Okay. Okay. Okay.
Okay. Any other questions or concerns? Right, so let's go back to our generation theorem. Is the generation theorem clear to everybody? Do you see why this is called a generation theorem? Right? You can start from K4, keep adding edges, expanding vertices of degree 4 or more, and get your desired 3 connected graph. And then you can go in the reverse direction by deleting and contracting edges. Okay? Good. This theorem is very useful. I call it a corollary because it follows from other results. But it has its limitations, especially because for many problems in graph theory, multiple edges and loops do not really matter. Basically, they don't they don't really affect the problem. For example, a graph has a certain property, could be planarity, which we will discuss next time, if and only if the underlying simple graph has the same property. So in such results, you don't care for parallel edges and loops. But when you construct this sequence, even if your original graph is simple, the intermediate graphs may not be simple. There is an example here. Notice that this graph that we started with is a simple graph. The next graph is again simple, but the last graph we got is not simple. This one. So the limitation of Thomason's theorem is that even if you are trying to prove something on simple graphs, you need to deal with graphs with multiple edges. And that can create problems when you're trying to prove things by induction, because you have to do more case analysis. Okay? And you will see this when you try to do writing exercise 1. Okay? But right now you don't have an example, so you may not be fully convinced about this. But when you try to prove results, you see that multiple edges create sort of annoying problems. And you need to deal with a lot of cases in order to handle multiple edges. So for this reason, it's natural to ask, can we get a similar theorem, but instead of 3 connected graphs, we have only simple 3 connected graphs? Can we get something similar for 3 connected simple graphs? Okay. The answer to that question is, yeah, go ahead.
Sir, I have a question. So if a given graph G is 3 connected, then can we say that its underlying simple graph will be 3 connected?
You tell me. Look at the definition of vertex connectivity and tell me what you think.
I think it will be 3 connected.
It is, yeah, and it is true for all K connected graphs. Multiple edges and loops do not affect K connectivity. They do affect K edge connectivity, but they do not affect vertex connectivity.
Vertex connectivity. Okay, so if we start with the simple graph G, which is 3 connected, and then by Thomasons theorem, we know that there exists an edge whose contraction gives us a 3 connected graph. But that graph, if it is not simple, then we can look on its underlying simple graph.
Right. Yeah, that is a good point. That is a good point. What is the problem? Okay, so that is a very good point. What Ananya is saying is, you take a 3 connected graph G, you contract an edge, you will get a smaller 3 connected graph. If it has multiple edges, you throw away the multiple edges. Now you have a simple 3 connected graph, right? So why do you need another theorem? That's a very good point. There is one problem. It's, yeah. So in a good induction tool, what you want is that the smaller object should not be much smaller than the bigger object. Okay, so you have a 3 connected graph G, you're trying to get a smaller 3 connected graph, but generally in a good induction tool, you want the smaller graph to have the size which is as close to the bigger graph as possible. Why? Because then you can easily argue about the bigger graph by understanding the structure of the smaller graph. And notice that when you contract an edge or when you delete an edge, you only lose one edge. Okay, so I'm looking at the number of edges. In contraction, you also lose the number of vertices by 1. But if you just look at the number of edges, it goes down by exactly 1. Okay? So, if you throw away all the multiple edges, you could get a lot of multiple edges, for example. So then the difference between the two graphs is going to be too big. And that makes proving things by induction harder. Okay? So in many induction proofs, you would have seen when you deal with integers, you go from k to k minus 1. You don't go from k to k minus 100 because it becomes very difficult to argue for k if you just know something about k minus 100. Okay, so that is an analogy. Okay, does that answer your question, Aranya?
Yes, sir. Yes, sir.
Right. So we want a theorem which removes only one edge but preserves the simple three connected property.
Okay. Okay. So, sir, if we contract an edge and if we look at the underlying simple graph, then the difference in the number of edges between those two graphs could be as large as possible.
Potentially, yes. Yeah.
Potentially.
I mean, you can bound it by some number like number of vertices or something, but that's not a very good bound.
Okay. So what we want, so if we want to prove a result for a graph with k edges, we want to assume it for k minus 1 only, not
Something
for k
like,
minus
yeah,
100 or
that's the
1000.
idea. We want to get a smaller graph that is as big as possible.
As big as possible. Okay.
Yeah. Okay.
Okay.
Good.
Then there will be a problem. Okay. Sir.
Okay. Does everybody follow this reasoning? Okay. So we want a theorem, similar theorem for simple three connected graphs, and we want our graph to be smaller only by one edge, like Thomason's theorem. So that brings us to another very important theorem in structural graph theory called Tuts wheel theorem. So before I state the theorem, so this is just Thomason's theorem. I copied it here before the lecture. Before we look at Tuts wheel theorem, let's talk about wheels. So these graphs are called wheels. Okay, you take a cycle on at least 3 vertices and you put a vertex and join it to all vertices on the cycle. This vertex in the center is generally called the hub of the wheel. We will denote it by H. Okay, I'm not going to write down the definition. So there is a cycle and there is a universal vertex as in your assignment 2 definition. Okay?
Sir?
Yeah.
Is wheel a universal definition or is it just something that we use for now? Can we directly...
No, wheels are a standard definition in graph theory. So yeah.
Okay.
Yeah.
Okay. Nice.
Okay. So
Okay.
yeah. If you allow wheels with multiple edges, then you have to specify that. But typically when you say wheel, it means a simple wheel. Yeah.
Okay. Okay.
Sir,
Yeah.
can you just repeat for the last 2 minutes what you said? Actually, I got disconnected.
You can just take a look at the video again. Okay. I don't want to repeat things, but I haven't said anything important. I just defined what a wheel is. You have a cycle and a universal vertex.
Okay.
Okay. So let's look at the wheels. By Thomas, these are 3 connected graphs.
So basically, the universal vertex is adjacent to every vertex on the cycle.
Yeah, that's right.
And a cycle, okay. So the okay.
Yeah.
So basically, these graphs are wheel graphs, right?
Yeah.
Okay.
Okay. So wheels are 3 connected. So you can apply Thomason's theorem, and you will find some edge you can contract and get a smaller 3 connected graph. So these edges are generally called the spokes of the wheel. Okay. So partial H, these edges are called the spokes of the wheel, and the other edges, E minus partial H, these are called the rim edges. Okay. So if you look at any spoke edge and you contract it, what will you get? Will you get a 3 connected graph? I would like you all to use some imagination and tell me what you get.
Sir, are you conducting a spoke edge or a rim edge?
Yeah, spoke edge.
Spoke edge, okay. So wheel is 3 connected, right?
Yeah. Supposing F is a spoke, then what can you say about G contract F? Is it 3 connected or is it not 3 connected? Right, so F could be this edge if you like.
Yeah, 3 connected.
Sorry?
Oh, one
I
second,
think
sir.
it is 3 connected.
One second.
Someone is saying it is 3 connected.
Sir, I think it will be 3 connected.
Make a drawing and check it.
No, sir, no, sir. It will not be 3
Not
connected.
3 connected. Good.
Because I have found a 2
It
hot
is not. It is not 3 connected. Okay, so everybody can check on your own. Do it yourself. Okay.
3 connected, sir.
So this graph
So
will not be
basically,
3 connected.
there will be 2 vertex cut. There will be
Yeah,
2
yeah,
vertex cut
that's right,
containing the
Yeah.
vertex each.
Yeah.
On the page.
Okay. So the spoke edges are not good because they don't even preserve 3 connectivity. Now let's look at a rim edge. Can somebody look at a rim edge and tell me what happens? Supposing E is a rim edge.
Yeah, it should be 3 connected, I guess.
Right. What do you get actually? Do you get a smaller wheel?
You get a wheel with extra spoke.
With a spoke,
Yeah.
extra spoke, yeah.
Extra
So in this case, G contract E is a wheel with multiple edge. Okay. So you get a 3 connected graph because wheels are 3 connected. There is a small assumption you need to make. The graph has at least 5 vertices because otherwise you have K4, and in the case of K4 you will not get a 3 connected graph. Okay, but we don't care about K4. So we are looking a graph on at least wheel on at least 5 vertices, and now you will get a smaller wheel with multiple edges, but in this case the graph is 3 connected because it is a wheel. Okay, so what is the conclusion? Because there are only 2 types of edges, spoke edges and rim edges, the conclusion is that for every edge, if you contract it, either you lose 3 connectivity or you maintain 3 connectivity, but then the graph is no longer simple. So, conclusion that for every edge of a wheel, either G contract E is not simple or G contract E is not 3 connected. Okay?
So here every edge belongs to a triangle, right?
Every edge belongs to a triangle here. Yeah, that's right. Okay? Good. So, we want a theorem similar to this corollary that I've written down here. We want a theorem where we have a simple 3 connected graph, and we want a sequence of simple 3 connected graphs with the same properties as before. The smallest graph is going to be K4, the last graph is going to be the graph G, and every graph is obtained from the previous graph by adding an edge or expanding at a vertex of degree 4 or more. And the same as before, in the reverse direction, every previous graph is obtained from the next graph by contracting edge or deleting an edge. Okay? What is the problem? We cannot insist on this condition because the wheels do not have any edge with the property we want. Right? So this theorem is false. Right? This is a false statement. It turns out if you let G0 to be any simple wheel or a wheel, because wheels are simple by definition, then you get this theorem. So if you just allow the smallest graph to be in the class of all wheels, maybe I shouldn't put the set notation. G0 is in the set of wheels. Then this becomes a theorem. Okay? And this can be viewed as a generation theorem for simple three-connected graphs. Okay? Notice that we just need to prove the converse direction. We just need to prove that, sorry, which direction? If you have such a sequence, then the graph will be simple and three-connected. That is clear by theorem 9.12. We need to prove the forward direction. We need to show that for every simple three-connected graph, which is not a wheel, there exists an edge E that can either be deleted or it can be contracted to get a smaller simple three-connected graph. Okay, so that is called Tuts wheel theorem. Every simple three-connected graph G has an edge E such that at least one of G delete E and G contract E is also simple and three connected, unless your graph G is a wheel. Okay, and so if we prove this theorem, then the above theorem, it follows. This follows from theorem 9.12, which was easy, and Tuts wheel theorem. Are there any questions?
Sir, why exactly can't wheel can be generated from K4?
Well, because first of all, from K4 you cannot generate anything interesting, because K4 is simple. So you can't, and it has no vertex of degree 4. So you cannot expand a vertex of degree 4 because there is no vertex of degree 4, right? And you also cannot add any edge because all edges, all vertices are connected to each other, right? So from K4 you cannot generate anything. Do you agree? I want to maintain the simple property, right? Right.
Yeah, but we can make a multiple edge and then expand a vertex of degree 4, right?
Yeah, but that is the whole point. I mean, I don't want to get multiple edges at all, because there are applications where you only care for simple three connected graphs. And if you have an induction tool that deals with, that leads to multiple edges, then proving the result requires a lot more case analysis. But again, its utility you will only see when you try to do writing exercise 1.
I see.
Okay, so I'll just say the following. We will prove this, but before that, I will say that the writing exercise 1 is an application. It is largely an application of Tuts wheel theorem. And what you can try is you can try to do it using Thomasons theorem and see that it is much more difficult.
So, like, so the result is that wheel cannot be generated from K4, right?
Right, unless you add multiple edges. But I think you are missing the main point of the result. The main point of the result is that all three connected simple graphs can be generated from some wheel. That is what you want to focus on. It's not
Without
that wheels,
without
right,
having
exactly.
multiple edge in some
Exactly.
intermediate graphs. Okay.
Right. So there exists some wheel. It doesn't, we don't know how big that is. That is actually related to Seymour splitter theorem, but I'll tell you about that
I
later.
see.
So for any three connected simple graph, G, there exists some wheel. So you can start from that wheel and just keep adding edges and expanding vertices, never creating multiple edges, and get to your final graph G.
Okay.
That is the key point of this
I
theorem.
see it now. Yeah. Okay. Thank you.
Okay? Good. All right. Any other questions or concerns? Is the result statement clear to everybody? Right? We haven't proved it. We will prove Tuts wheel theorem tomorrow, and that will
I
be
did
the
not
end
see
of
that you
module 1.
added the word simple there. That's what.
Okay, where?
The simple word that you added above three.
Okay. Yeah.
So the theorem that we wrote for three connected graph was 2, but if we add the simple this thing, it's no longer true.
Exactly.
Okay.
Exactly.
Okay.
We want simple everywhere. Okay. Good. Any other questions or concerns? So tomorrow we are going to prove Tuts wheel theorem. I will give you some do-it-yourself and try-it-yourself exercises so that you can observe some easy things before tomorrow's lecture, and that will be the end of module 2. And Monday we will start plenarity. Also, Tuts wheel theorem is not in Bondi Murthy, which is why I'm not numbering these results. So the proof is not in Bondi Murthy.
So thank you, sir. Can I leave?
Okay, yeah. Please feel free to leave. In fact, I'll stop recording now. So feel free to leave the meeting.
Okay, sir. Thanks.